Welcome to NPTEL MOOCs course on Computer Vision and Image Processing, Fundamentals and Application. So, in my last class I discussed about some fundamental concepts of computer vision, and also I have highlighted some applications of computer vision. So, in my class today I will discuss the introduction to digital image processing. So, what do you mean by digital image? So, I can say digital image means 2D array of quantized intensity values, or maybe the 2D array of numbers. So, digital image processing means how to manipulate these numbers. Suppose if I want to improve the visual quality of an image, then in this case I have to manipulate these numbers. These numbers means the quantized intensity values. And suppose if I want to remove noises, then also I have to manipulate these numbers. So, manipulation of these numbers is mainly the image processing. In case of the image acquisition, the light is converted into electrical signal. So, I am getting analog signal, the analog image. The analog image can be converted into digital image by the process of sampling and the quantization. So, I have to do the sampling along the x direction and sampling along the y direction, and that is called the spatial sampling. After sampling, I have to do the quantization of the intensity values. So, to convert an analog image into digital image, I have to do sampling and the quantization. So, what is digital image? I will show you. Digital image processing means processing of digital images on digital hardware, usually a computer. So, this is the definition of digital image processing, that is the manipulation of the quantized intensity values, the manipulation of the numbers. Now, here I have shown a typical digital image processing sequence. So, if you see, the light is coming from the source and it is reflected by the object, and I have the imaging system. So, this imaging system converts the light photon into electrical signal, and in this case I am getting the analog image. So, analog means it is a continuous function of time. To convert the analog signal, the analog image into digital, I have to do the sampling and the quantization. So, sampling in the x direction, sampling in the y direction, and that is called spatial sampling, and after this I have to do quantization of the intensity value. After this I am getting the digital image. This digital image I can store in the digital storage, I can process the image in the digital computers, I can display the image, the process image, and I can store the image. So, this is a typical digital image processing sequence. The same thing I have shown here in this figure. So, image sensors are available for image acquisition, and after this I will be getting the digital image, and that digital image I can process by image processing hardware, and I have also image processing software. So, the process image can be displayed and it can be stored. This is the components of a general purpose image processing system. The concept of image formation here I have shown, and the light is coming from the source and it is reflected by the surface. So, I have shown the surface normal also. So, suppose this is my surface normal, and I have the optics is mainly the camera. So, light is reflected by the surface and I am getting the image in the image plane, that is the sensors. So, sensor means it converts the light photon into electrical signal. This pixel intensity value depends on the amount of light coming from the surface. So, if I consider one pixel at this point, this pixel value, the pixel intensity value depends on the amount of light reflected by the surface. So, that means that the pixel value actually depends on the surface property. The surface property is called the reflectance property of the surface, that is the amount of light reflected by the surface. So, this is a typical image formation system. So, I have shown in this case, this is the electromagnetic spectrum, the source of illumination. I have shown the gamma rays, X-rays, ultraviolet, infrared ray, microwaves, FM radio, and if you see the wavelength from 400 to 700 nanometers, this is the visible range of the spectrum, the electromagnetic spectrum. So, based on this source of illumination, I may have this type of images, maybe the digital photo, the image sequence used for video broadcasting, and something like the multi-sensor data like satellite image, visible image, infrared images, and an image of the obtained from the microwave bands, medical images like ultrasound, gamma ray images, X-ray images, and the radio band images like the MRI images, astronomical images. So, based on this electromagnetic spectrum, I may have this type of images. So, here I have given some examples. The first one is the X-ray, and next one is the photo that is obtained in the visible region of the electromagnetic spectrum. The next one is the infrared image, another one is the radar image. So, this is the radar image, ultrasound image, and the mammograms. So, different types of images. And some of the applications of image processing here I have shown the applications like in multimedia, medical imaging, that is medical image processing and medical image analysis. I have many applications, even in the forensic and the biometrics like the fingerprint recognition, the iris recognition, video surveillance, remote sensing. There are many applications of image processing. And one important application of image processing is image fusion. If you see, I have considered in the first example, I have two images, one is the MRI image, another one is the PET image. So, these two images are fused and I am getting the fused image. So, that means the important information from MRI images and the PET images we have considered, and the redundant information I am neglecting, I am not considering. So, this is the fused image. In this fused image, I have more information as compared to the original source images. So, I have two images, one is the MRI image, another one is the PET image, and the fused image I am getting from these two images. In the second example, I have considered the IR image and the image of the visible region of the spectrum. These two images I am fusing and I am getting the fused image. So, it has more information as compared to the source images, and in this case you remember that I am neglecting the redundant information, I am not considering the redundant information. So, these are the applications of image processing. So, what is analog image? Analog means it is a continuous function of time, and this is the definition of the analog image. So, here I have shown one analog signal that is obtained from the camera. So, I have the horizontal lines and the vertical the blanking signals. This is the mainly the video signal. So, this analog signal can be converted into digital signal by the process of sampling and the quantization. So, in TV standard, I know some of the standard like the PAL, the phase alternating by lines. So, this is one TV standard. Another standard is NTSC, this is another standard. Another standard is SICAM. So, I am not going to discuss about this, but in India we use the PAL systems. So, in the PAL system we have 625 lines. 625 lines, and in this case we have considered the 25 frames per second, 25 frames per second in phase PL system, the phase alternating lines. This is a TV standard and we have considered 625 lines and 25 frames per second. In NTSC generally we use the 30 frames per second. So, I am not going to discuss about the TV standard. Now, let us consider, suppose a video signal I am considering, and suppose the bandwidth of the video signal, I am considering, suppose it is 4 megahertz. Let us consider this example, 4 megahertz. So, what will be my sampling frequency then? Bandwidth is 4 megahertz. So, sampling frequency will be my 8 megahertz as per the Nyquist sampling theorem. So, my sampling frequency will be 8 megahertz. Now, I want to count the number of pixels per frame. So, I want to count the number of pixels per frame. So, how many pixels per frame that I want to determine. So, 8 megahertz, 8 into 10 to the power 6, that is samples per seconds, divided by, I am considering 25 frames per second, 25 frames per second. So, this will be equal to 320 0 0 0. This is the digit pixels per frame. Pixels per frame. Pixel per frame. So this is approximately the 512 into 512. So that means the image size will be 512 into 512. The image is represented by m cross n. This is the size of the image. The image is represented by m cross n. This is the image because it is a 2D array of numbers. So I have m number of rows and n number of columns. So my rows are like this. These are my rows, and I have the columns like this. So the image is represented by m cross n. So in this example, I have seen that the size of the image will be 512 into 512. So this I have shown this example. Now this already I have explained how to get the digital image. So in this diagram you have seen that I have shown one continuous tone image, that is the analog image, and after this I have to do the sampling along the x direction and the sampling along the y direction I have to do, and after this I have to do the quantization of the intensity values. So I have done the quantization, and after this I am getting the 2D array of numbers. So this is a sample and the quantized image I am getting. So this is a representation of a digital image. The same thing I am showing the sampling and the quantization. So sampling along the x direction and the sampling along the y direction I have shown, and after this I am doing the quantization of the intensity value. So sampling the 2D space on a regular grid, and after this I have to quantize each sample value. First I have to do the sampling, and after this I have to do the quantization. So this is first I am doing the sampling, and after this I am doing the quantization. So it is a 2D array of numbers, and this is the digital image. So I have shown the values. The value is the 0 is the grayscale value, the 34 is the grayscale value, this 102 is the pixel value. So I am considering this is one digital image. And in this case already I have shown the image is represented by m cross n. M cross n is the size of the image. So m cross n is the size of the image. So here I have shown the rows, the m number of rows I am considering, and the n number of columns starting from 0 to n minus 1 and 0 to m minus 1. And this is the origin of the image. That is, the point is 0 0. And I have shown the pixels. These are the pixels of the image. These are the pixels of the image. Now let us consider the neighborhood of a pixel. So in this figure I have shown a particular, suppose pixel, the pixel is p, and this pixel I am considering p. I have shown two cases. One is the neighborhood, the 8 neighborhood I have considered. Corresponding to the first case, I am considering the neighborhood pixel, the p1, p2, p3, p4, p5, p6, p7, p8. That is called the 8 connected neighborhood. In the second case, if you see the neighborhood pixel, I am considering p2, p4, p6, p8. Corresponding to the center pixel, the center pixel is xy. This is center pixel. So if you see here, the first one is the 8 connected neighborhood. This is the 8 connected neighborhood. 8 connected neighborhood. The second one is the 4 connected neighborhood. The 4 connected neighborhood. So this 4 connected neighborhood I can write like this, and 4p, 4 connected neighborhood. So this pixel I have to consider, this pixel I have to consider, this pixel I have to consider, this pixel I have to consider. That means it will be x, y minus 1, that is the 1 pixel, x, y plus 1, x plus 1, y, x minus 1, y. So this is the 4 connected neighborhood. Similarly, you can define the 8 connected neighborhood. So in the this is the neighborhood of the 4 connected neighborhood, the second one is the 8 connected neighborhood. Now you can see corresponding to this neighborhood I can determine the Euclidean distance, the city block distance and also the chessboard distance. So how to define the distances? This Euclidean distance, it is defined like this. Euclidean distance. Euclidean distance is suppose DE, Euclidean distance is DE. So suppose I am considering 2 points IJ and KL. So it is I minus K whole square plus J minus L whole square 1 by 2. This is the Euclidean distance. Another distance is L1 distance, that is called the city block distance. City block distance. The city block distance I can show, it is suppose the D4 distance, city block distance suppose. So it is the distance between IJ and KL. So it is I minus K absolute value and absolute value J minus L. This distance is called the L1 distance. It is the city block distance or it is called the L1 distance. L1 distance. The another distance is the chessboard distance. Or sometimes it is called the Chebyshev distance. So I can define, suppose that it is D8 between 2 pixels I and J KL. So I have to consider this distance. The distance is maximum value I have to determine I minus K and J minus L. So these distances I have defined, one is the Euclidean distance, one is the city block distance, another one is the chessboard distance. So corresponding to these distances, you can see in the first figure, this figure, I have determined the distance between the center pixel is this pixel and the neighborhood pixels. You can see the distance is 1.41 to the diagonal pixel, and to this pixel it is the distance is 1, to this pixel it is 1.41, like this I am getting the distances. All the distances I can compute to the neighborhood pixel. Similarly, if I consider the city block distance corresponding to the center pixel is this, I can find the distance between the neighborhood pixel. So if I find the distance between the center pixel and this pixel, the distance will be 2, this distance will be 1, this distance will be 2, like this I am determining the distance, I am calculating the distance. In the third case, I am considering the chessboard distance. So corresponding to the center pixel, this center pixel, I am determining the distance between the neighborhood pixels, and in this case I am getting 1, 1, 1, 1 like this distance I am getting. So you can see these distances I can compute. So I can give one example. Suppose if I want to determine the distance between the 2 points A and B, and that is the suppose the Euclidean distance I can determine between 2 points XA minus XB, I can determine like this whole square plus YA minus YB whole square. So suppose this XA is XA is suppose 70 minus 330, suppose XB is 330, I am taking one example, whole square plus suppose this YA is 40 and YB is 228, suppose whole square. So this value I am getting, it is 335, almost 335, this value is 335. This is the Euclidean distance I can determine. and L1 distance, if you can compute L1 distance, then this distance will be DAB will be, you can see this is XA minus XB plus YA minus YB. So you will be getting the value something like 448. Also you can determine the chessboard distance, also you can determine. The chessboard distance DAB between 2 points, that's maximum you have to take, and it is XA minus XB YA minus YB. So this value you will be getting something like 260. You can verify this one. So in this example I have shown how to calculate the Euclidean distance, city block distance and the chessboard distance. So this is the important, the neighborhood of the pixel, a particular pixel. So what is digital image? The digital image is nothing but the 2D array of numbers representing the sample version of an image. The image defined over a grid, and each grid location is called the pixels. So I have shown the pixels, these are the pixels, and represented by a finite grid, and each intensity data is represented by finite number of bits. So that concept I can explain like this. Suppose the image is represented like this, m cross n. The size of the image is m cross n. That is, m means the number of rows and number of columns. And the grayscale value, suppose I am considering L number of grayscale value. So 0 to L minus 1 grayscale value, that can be normalized between 0 to 1. Suppose the L number of grayscale levels, L is equal to 2 to the power k. So now the number of bits required to store an image is equal to m cross n cross k. That is, the number of bits required to store an image is equal to m cross n cross k. Now what is the definition of the dynamic range? Suppose I have an image, the highest pixel value and the lowest pixel value I know. So the difference between this is called the dynamic range. The contrast of an image depends on the dynamic range. So for a good contrast image, the dynamic range will be more. Now the resolution of an image, So how to define the resolution of the image? So one resolution is the spatial resolution. The spatial resolution means, I can say, the number of pairs of lines per unit distance. This is the definition of the spatial resolution. And another one is the intensity resolution. So intensity resolution, I can say the definition is smallest discernible changes in the intensity level. So suppose if I consider 8 bit, so 2 to the power 8 is equal to 256. That means how many intensity level I am using? The 256 numbers of intensity level I am using. So spatial resolution means the number of pairs of lines per unit distance. That means, so how many pixels, if I consider these are the pixels, so how many pixels per unit distance, that is called the spatial resolutions. And intensity resolution means the smallest discernible changes in the intensity level. So how many intensity levels I am using, that is the intensity resolution. And if I consider the video, in video I have to consider, suppose if I consider a video, in video I have to consider how many frames per second. How many frames per second, that corresponds to the temporal resolution. So for video I have temporal resolution, and for the image I have spatial resolution and the intensity resolution. So here I have shown that pixels and the intensities. This is the two-dimensional array of numbers, and here I have shown the pixel value 255, 18, 19. So these are the pixel values. And for the binary image is represented by 1 bit. So that concept I can show you. So already I have defined the resolution of an image. One is spatial resolution, another one is intensity resolutions. So suppose if I consider, suppose 0 to 255 levels, 0 to 255 levels. So how many bits we need? For this we need 8 bits. And if I consider 0 to 127, then I need 7 bits. If I consider 0 to 63, then in this case I need 6 bits. If I consider 0 to 31, then in this case I need 5 bits. If I consider 0 to 15, then in this case I will need 4 bits. If I consider 0 to 7, then I need 3 bits. If I consider 0 to 3, I need 2 bits. And if I consider 0 to 1, only 2 levels, 0 to 1 means 2 levels, so I need only 1 bit. So this is called a binary image. Binary image. So this is the binary image. So binary image needs only 1 bit. So a binary image is represented by 1 bit, and the gray level image is represented by 8 bits. And the image is represented by fxy. What is fxy? Fxy means the intensity at a position, the position is xy. This is the definition of image. The image is represented by fxy. So here I have shown the image as a function, because image is nothing but it is fxy. Fxy. So the intensity value I have shown fxy here. And there is another definition of digital image. In this definition I have shown the rows and the columns. So I have shown the pixels. So in this definition, if you see, the image is represented by these parameters. One is x and y coordinate, that is the spatial coordinate. And if I consider the stereo image, then one important parameter is the depth information. So z corresponds to the depth information. So suppose if I have 2 images obtained by 2 cameras, so from 2 images I can determine the depth information. So in this case the z represents the depth information. And if I consider the color image, so lambda means the color information. And if I consider the video means the number of frames per second. So I have to consider temporal information. So t is the temporal information. So image is represented by x, y, z, lambda t. X and y is the spatial coordinate, z is the depth information, lambda is the color information, and t is the temporal information. And that is one definition of digital image. And some of the typical values, number of rows, number of columns, the 256, 512, 525, 625 like this. These are the number of rows, number of columns 256, 512, and gray level values something like 264, 256 like this. We have the values. And in this case I have shown the dimensionality and the resolution of an image. So, in this case I have shown the image is 2 dimension, and another case I have shown 3 dimensions, that is for the video, x and y coordinate, and another one is number of frames per second, that is the temporal information. So, here I have shown the dimensionality and the resolution of an image. So, image is 2 dimension and video is 3 dimension. So, in this example I have changed the spatial resolution. If you see the first image is 256 into 256 pixels. The second image is 128 into 128, this image. The third image is 64 into 64. So, that means I am decreasing spatial resolution, and because of this I am getting some effects like checkerboard effect. This effect I have observed here. This is called the checkerboard effect because I am decreasing the spatial resolution of an image. Now, I am considering changing the intensity resolution, that is called the gray level resolution. So, first example is I am considering the 8-bit image, next one is the 4-bit image, next one is the 2-bit image, and 1-bit image is nothing but the binary image. So, I am changing the gray level resolution, the intensity resolution. This is another example. The initial, if you see the first image, this is 16 gray levels, second one is the 8 gray levels, the next one is 4 gray levels, and this is the 2 gray levels, that means the binary image. So, if you see this, that this portion suppose if I consider, this portion is not properly represented in these images, So, this effect is called the false contouring effect. So, I have two effects, one is the checkerboard effect, that is because of the spatial resolution, and another one is the false contouring effect because of insufficient number of intensity levels. So, I have given these two examples. The image types I have shown here. I have RGB image, the grayscale image, and the black and white image, that is the binary image. So, in case of the color image, corresponding to a particular pixel, I have 3 components. One is the R component, that is the red, another one is the G component, that is the green, and the blue component, that is the B. So, RGB value, that is the primary colors. So, corresponding to a particular pixel, I have 3 components, R component, G component, and the blue component. And this particular pixel is called the vector pixel because I have 3 components. So, this is one example of the binary image. Basically, the binary is 1 and 0 only. So, if I apply the edge detection principle, or edge detection, then in this case I will be getting the binary image. So, this is one example of the binary image. The next example is the grayscale image. So, in this case I am considering 256 numbers of intensity levels, and if you see, it is the grayscale image. And after this I have considered the color image. So, this is the color image because this is called the vector pixels. In the vector pixels I have 3 components, R component, G component, and the blue components. And now I have different types of color models. I will discuss about the color models like RGB color model, YCBCR color model, HSS color model. So, all these color models I will discuss in the color image processing because I need 8 bits for the R components, 8 bits for the G component, 8 bits for the B component. So, it is called 24-bit video, that is the color image. And this is the example of the true color image. Here you see corresponding to a particular pixel, I have the red pixels, the green pixels, and the blue pixels. So, that means pixel means the red information, green information, and the blue informations corresponding to a particular pixel. The red value, green value, and the blue value. Another definition of index image. So, for the index image, I have one color map. So, this is a color map. So, this is something like a lookup table. So, corresponding to this value, we have 3 values. One is the R value, this is R value, like this G value, and the B value. 3 values are available. So, corresponding to this one, corresponding to this RGB value, the index number is 6. Okay, and like this, I have all the index numbers. So, this is the index image. If you see, so I need a color map, and in the color map, you see the index number is associated with the color values, R value, G value, and the B values. So, corresponding to 6, I have these RGB values. So, types of digital image. So, binary image 1 bit per pixels, grayscale image 8 bit per pixels, true color or the RGB image, it is 24 bit per pixels, and for index image 8 bit per pixels. So this is the case. So next one is, what is image processing? The image processing is that manipulation and analysis of the digital image by digital hardware, okay, and it is for the better clarity, that is for the human interpretations, and automatic machine processing of the scene data. So that is image processing. So I have given some examples here. So one is image enhancement. Image enhancement means to improve the visual quality of an image. So first, if you see, I am just compare the two images, the input image and the output image. You can see that I am improving the visual quality of the image. So some of the examples, like I can increase the contrast of an image, I can improve the brightness of an image. Like this, I can do many things. That is one example. In this example, another example, I am doing the image enhancement. So first one is the input image, the second one is the better quality image, that is the enhanced image. In this example, I am considering the blurred image. So blurred image may be because of some motion blur. Suppose the camera is moving, then in this case I am getting the blurred image, and in this case I can apply some image restoration technique to de-blur the image. So in this example, I have the blurred image and I can apply some image restoration technique to get the de-blur image. In this example, I have considered a noisy image, and after this I am getting the filtered image, the better quality image. Now the image processing, what is actually image processing now I can show, because image is represented by fxy. What is fxy? Intensity at the point is x comma y. Now in this case I have gxy is the output image and fxy is the input image. So I can change the range of an image or I can change the domain of an image. What do you mean by range of an image? The range of an image means I can change the intensity value, the pixel value I can change by using some transformation. Also I can change the domain of an image. Domain of an image means I can change the spatial positions, x and y coordinate I can change. One is just changing the range of an image and another one is just changing the domain of an image. So in this example, here you see I am changing the range of the image, that means I am changing the intensity value. In the second case, I am changing the spatial coordinates. So I have shown the two examples. The first one is the input image, this is the input image, and I am changing the range of an image, that is the pixel values. In the second example, this is the input image and I am changing the domain of the image. In this case, I am doing the scaling of the image. So that means this is the changing the domain of the image and this is the changing of the range of an image. This is one transformation. If you see, I am doing some mapping. This pixel is mapped to this point, this pixel is mapped to this point. So this is my input image and this is my output image. So I can do the mapping. That means I am changing the spatial coordinates. I can do rotation of an image. This is the rotation of an image. I can do the scaling of an image. That means I can change the domain of an image. I can change the spatial position of the pixels. Now the linear point operation on an image. So I can give one example here. Here you see Gn is the output image, Fn is the input image, and in this case I am considering one operation. The operation is H. That is called the point operation, the linear point operation. The point operation is mainly the memoryless. We don't need any memory. Now in this case, Gn is equal to, I can consider Gn is the output image, P into Fn plus K. So if I consider this expression, K is the offset and P is the scaling factor. Now based on this the point operation, how to get the negative image? So in this case, if I consider P is equal to -1 and K is equal to L minus 1, L means the number of gray level values, how many levels I am considering, from 0 to L minus 1. So output is Gn minus Fn plus L minus 1. So if I consider this transformation, then in this case I will be getting the negative image. So this is my input image and then this is my output image. Also I can apply the nonlinear point operation, maybe the logarithmic operation I can apply. So this point operation I am going to discuss after 2-3 lectures, that is when I will discuss about the image enhancement technique. That time I will discuss about the point operation. So this is about the non-linear point operation and the linear point operations on image. Here I am giving one example, the addition of images. So n number of images I am considering. After this I am doing the addition of n number of images. The second example is the subtraction of 2 images. If I do addition of the images, what will happen? You see, I have the noisy image. Okay, suppose I have number of noisy frames. If I do the averaging, then in this case the noise can be reduced. Image averaging for noise reduction. So just I am adding this one. That means I am actually averaging the images. That is, I am doing the sum of n input images, and corresponding to this I am getting this example. So in this example, the image averaging for noise reduction. And already I have explained that how to find the difference between 2 images. So one example is, suppose if I consider these 2 images, the first image is this. In this case the background is available. In the second case the background and the foreground is available. Suppose the moving objects are available in the image. In the first case there is no moving objects, and in the second case suppose the background is also there, the moving object is there. So in this case if I do the subtraction of these images from the first image to second image, then in this case I will be getting the foreground, something like this. Moving objects I can determine. That is called the sense detection. So this is called the principle of the sense detections. Thus I have to subtract the images. Then in this case I will be getting the moving objects in the image. Like this we can do some geometric image operations. So I can do image translation like this. I can change the coordinate is n1, another one is n2. So I can do the translation of the image. The coordinate is x and y actually. In this case I am showing n1 and n2. So n1 minus b1 and n2 minus b2. That means I am doing the image translation. The second example is also, if you see, the coordinate n1 is divided by c, the coordinate n2 is divided by d. So that means I can zoom the image, zoom in and the zoom out I can do. I will explain this one, zoom, later on. So this is also geometric image operation, and this is one example of the image rotation, that I can rotate the image. So for the rotation, the transformation matrix is cos theta minus sin theta, cos theta. So by using this transformation matrix you can rotate an image. Here I have, in this example I have shown the zoom. After zooming I have done some interpolation. Nearest neighbor interpolation it is done. The second case is the bilinear interpolation, that is more accurate. So I have shown 2 interpolation techniques. One is the nearest neighbor interpolation, another one is the bilinear interpolation. After zooming, so image processing steps I have, one is the image acquisition. After this I have to get the digital image. So for this I have to do the sampling and the quantization. Compression is important, because if I consider the raw image or the raw video, that is very bulky. So that is why for storing the image, for storing the video, or for the transmission of the image or for the transmission of the video, I have to do image compression, I have to do video compression. Next one is the image enhancement. Image enhancement is to improve the visual quality of an image. So one example is, I can improve the contrast of an image, or maybe I can improve the brightness of an image. That is image enhancement. And restoration is also, the meaning is same, to improve the visual quality of an image. So there is a basic difference between enhancement and the restoration. In image enhancement, that is mainly the subjective. It depends on the subjective preference of an observer. So I can say the image is not good, the contrast is not good, and based on my observation I can improve the visual quality of an image. That is subjective, and there is no mathematical theory for image enhancement. But in case of the image restoration, I have mathematical models. So I can give 1 or 2 examples like this. Suppose I am taking some image and camera is moving, then in this case I am getting the blurred image. So in this case I can de-blur the image by using the restoration principle, the image restoration principle. So, for this I have to develop a mathematical model, and based on this mathematical model I can improve the visual quality of the image. So, for this I have to apply image restoration. That is, image restoration is objective and image enhancement is subjective, the subjective preference of an observer. I can give another example of the image restoration. Suppose the object is not properly focused, then in this case I am getting the blurred image. Then also I can improve the visual quality of the image. I can de-blur the image. And suppose if I take one image in the foggy environment, then in this case I am also getting not good quality image. Then by using this image enhancement principle or the restoration principle, I can improve the visual quality of an image. So you see the fundamental difference between image enhancement and the restoration. In image enhancement there is no mathematical model, general model, but in image restoration I can develop some mathematical model, and by using this mathematical model I can improve the visual quality of an image. Next one is image segmentation. The image segmentation is the partitioning of an image into connected homogeneous region. Okay. So I can later on I will discuss about the image segmentation. So that means I am doing the partitioning of an image into connected homogeneous region. And after this, for computer vision I have to extract features, and after this based on the features I have to go for recognition, the object recognition, that is called the image interpretation or the understanding. So this is a typical image acquisition systems. So we have the CCD, the search coupled device camera. Here you see the CCD chips. So the photon is converted into electrical signal. After this I am getting the video signals. That is the analog signals. The analog signal can be converted into digital. Already I have explained about this. So this is the image sensor. The light photon is converted into electrical signal, and after this we have to do the sampling and the whole, and after this you can convert the analog signal into digital image. So these are the, for the still image, these are the 512 into 512 some typical values, 256 into 256 one typical values. For video like this 720 into 480, 1024 into 768, that is the high definition TV like this. And regarding the intensity resolution, 8 bits is sufficient for all, but the best applications needs 10 bits, television, production, printing. And for medical imaging, generally the 12 to 16 bits images we consider. So this is the case, and one important application is the medical imaging. So we need more number of bits, we need more number of intensity levels. And if you see why we need the compression, suppose a raw video is very bulky. So suppose in this example if I consider the digital video, uncompressed video, 1024 into 768, that is the size of the image frame. Suppose if I consider 24 bit per pixel, why it is 24 per pixel? That is the, if I consider the color image, that is the 24 bit per pixels, and 25 frames per second, that needs 472 Mbps. So that is very difficult to store, and also for transmission. So that is why we have to compress the image. The compression of the image is important in this case. So I have given this example. And image enhancement, already I have explained that to improve the visual quality of an image, like this we can improve the contrast, we can sharpen the edges, we can remove the noise, the image enhancement. This is already I have explained. One is enhancement, restoration, image restoration I have already explained, and reconstruction, mainly we have the 2D images. So if I want to get the 3D information, the reconstruction of the 3D information from the 2D projections, that is called the reconstruction. This concept I am going to explain maybe after 2-3 lectures, that is image reconstruction from 2D projections. That concept I will explain the radon transform. Radon transform I will explain later on. So construction of 3D information from the 2D projections, that is used in CT scan, the computer tomography. So this concept I am going to explain when I will discuss the radon transform. After this we have to extract the features, the image features I have to extract. maybe something like the color feature I can consider, texture I can consider, shape features, motion feature I can consider, and finally we will go for the recognition or the classification of the objects. That is the machine learning. This is the machine learning, feature extraction and recognitions. So these are some examples: the image filtering, original image, the noisy image, and the filtered image. So this is one example. Second example is the image restoration. Degraded image, after processing I am getting the restored image, that is a very good quality image. This is the noisy image. And for contrast improvement, there is a technique, that this technique also I am going to explain later on. That is, by histogram equalization technique I can improve the visual quality of an image. That means I can improve the contrast of an image. So this concept I am going to explain when I will discuss the image enhancement principles. This is one example of the contrast enhancement. This is not a good contrast image, this is not a good contrast image, but I think this is also good contrast image, I can say. So by using the histogram equalization technique I can improve the contrast of an image. And after this I have to extract features. The features may be something like edges I can consider, the boundary of an object I can consider. So I can extract many features from the image or maybe from the video. And after feature extraction, this one example is the edge detection technique. So this is my input image and I am extracting the edges of the image. And the segmentation is the partitioning of an image into connected homogeneous region. This homogeneity may be defined in terms of the gray value, color value, texture value, shape information, and the motion information. So based on this principle, based on these values, I can define the homogeneity. So again I am going to discuss about the segmentation principle. So suppose in my next classes, so suppose if I want to the partitioning of an image, so this is one partition, this is one partition, this is one partition. So this portion is homogeneous, this portion is also homogeneous. If I consider this portion is homogeneous, this portion is homogeneous, like this portion is also homogeneous. So homogeneity I can define in terms of gray value, color, texture, like this I can define. So corresponding to this region the gray value is almost same, or maybe the color may be same. So like this I can do the partitioning of an image. So this is one example of the segmentation, image segmentation. This is my image, input image, and after this I am doing the segmentation. And finally after feature extraction I will go for the object recognition. So this is my last step. That is, I have to extract the features. The features may be the color is a features, texture may be the features. So I can extract different types of features from the image, and after this I will go for the object recognition. So first one is the feature extraction, feature model matching, hypothesis formation, and object verification. I have to do this, and finally I will go for the image understanding. So maybe I can apply some supervised technique, and that is the part of the artificial intelligence or maybe the machine learning. So I am going to discuss about this in my last lecture, the machine learning. So this is the final step, the image understanding. So in this class I have discussed about the concept of image processing, what is the meaning of the digital image, and after this I have discussed about the types of digital image, the RGB image, the grayscale image, the binary image, index image. So I have discussed about this, and also the concept of the resolution of an image. So first I discussed about the spatial resolution, after this I discussed the intensity resolution, after this I discussed about the image processing techniques. So I can change the domain of an image, I can change the range of an image. So I have given some examples. I can do the rotation of an image, I can do the scaling of an image, like this I can do many operations. I can do zooming also. After this I have considered the typical image processing system, the computer vision systems. So first I have to do some image processing, and in this case before image processing I have to get the image. The analog image can be converted into digital image by sampling and the quantization. After this I can improve the visual quality of the image by using the enhancement and the restoration techniques, and after this I can extract the features from the image, and finally I will go for object recognition, that is the pattern classification or the machine learning techniques I can apply. So this is about the second lecture. So next class I am going to explain the concept of the image formation principle, and also I will discuss about the radiometry. Radiometry means the measurement of light. So let me stop here today. Thank you.